All right, so I think recording begins. So let's begin our lecture today. So we'll continue on from last Tuesday, right? Last Tuesday, about what are before we go into the single cycle architecture, we need to wrap up the topic on ISA first, right? So lecture one, we kind of briefly talk about the age of Moore's law. To quickly recap this, basically Moore's law can predict that we're gonna have more transistor, and they're gonna per chip, right? And it's gonna the size of the transistor is gonna get smaller, smaller, and smaller, right? So we can basically cram more transistor into your circuit, which allow us to do fancy things on your integrated circuits, or the CPU or the GPU that as you know it, that you buy and use it to work on your research or play games or watch movies, right? The other thing I talked about last week was about how basically if you look at a program, right, what actually happened beneath that we talk about the compute stack, which is something you see here, right? Many of you are going to work on the algorithm side, the program side, the compiler side, the runtime side, which also include network and handling the system, basically, right? And then what we're going to talk about today, and also for the majority of the class, to be honest, is from the ISA, which you can always think of ISA as basically the language that the chip or the machine is using to actually understand our command, right? Because at the end of the day, what we need to do is from the problem here, basically we're sending our command, right? To tell, hey, do this, do that, and do that to the computer. And the computer somehow need to understand that command. That bridge between the understanding and not understanding of our command is done through the ISA and the compiler. The compiler tries to translate the human program in whatever programming language that human writes into the language that machine understand, right? That language is dictated by the ISA. So that's the key point. Then based on the language, you can implement whatever hardware you want in the microarchitecture to actually implement the ISA. Okay. So we talk about from program to binary. You can have any source code from any different programming languages. As long as you can compile, then it will be compiled into something that machine understand. And when I say machine understand, it can be in any assembly languages, like the x86 or ARM, or even the language that we call MIPS, which is what we're going to use for your lab, right? It's one of the more, to be honest, it's a simple ISA, but it's also really, really powerful, right? And one thing I'll talk a little bit more about the lab is that the MIPS ISA is actually being used by many of the machines that you might have been using. Well, are you guys old enough to play the PlayStation 1? Or do we have a gap where me and Ajahn Susha, Ajahn Bak, I mean, we did grow up in that generation, but you guys are not. But that machine is actually using the MIPS ISA. Right, so you can see that there are different machines that use different ISA, and now it's kind of converging to x86 and ARM, and maybe RISC-V in the future, right? And these are the language that your CPU understand, your central processing units or your processor, right? And we talk about different trade-off. For example, some instruction can be complex, or I can design an ISA that just have a really simple instruction. I just want to do add, subtract, multiply, the basic things like logic and or, and then handling jump and branch, and that's it, right? And I will let the compiler handle the rest of the translation from your program all the way to the assembly language. That's also okay too, right? It can also support different features like multi-threading, lower power, lower memory, VLIW, which is what we're going to learn. I think kind of 3/4 of this class, we'll talk about this topic when it starts to introduce the GPU. And then it can be a complex ISA. Somehow we call this a CISC ISA. A sample of the CISC ISA are the x86 that you use in many modern processors, or a reduced ISA or RISC, right? A good example of a RISC ISA is the MIPS architecture that you use for the lab, and also the RISC-V architecture. That's actually one of the really popular open ISA available in the world. Like if you want to use the RISC-V, it's free. You can use it. Another example of reduced ISA is the ARM ISA, but ARM has some flavor of the complex ISA with some instruction as well. Now, there are some trade-offs with different complexity of your ISA. All right. If you look at the trade-off, a complex ISA basically means that I'm gonna have thousands and thousands of instructions, right? I might have an instruction to do fancy things that maybe doing matrix multiply if I want to, right? But here's the thing. Let's say I want to say, make sure the computer can use English. It means that I need to build the hardware to make sure they understand every single word in English, right? So if your language or your ISA is more complicated, my hardware need to support all this 1,000 instructions. Even though it may be one instruction that I never used it before, right? I'll use this example. And I'll use the Thai word for this, right? น้องคนไหนมีใครใช้ศัพท์ราชการบ้าง So basically that how many of you actually use the like government style wording when you talk in Thai ศัพท์ราชการที่มันอยู่ตามหนังสือราชการมีใครใช้ป่ะ เมื่อเทียบกับคำที่เราใช้พูดกันปกติภาษาไทยอันไหนใช้บ่อยกว่ากันครับ so the question basically between like a really official government Thai government I will pin to Thailand because they love to use really rare and weird wording that is not necessary, but how do you use that in everyday life as opposed to a normal spoken Thai language, right? So 99% of the time I'll communicate with people in Thai language, the normal spoken language. And then there'll be some rare cases where I need to draft the official letters and send it to the government. That's when I use this really corner case, super weird languages, right? But because I need to support in totality, I need to support the Thai language. I need to build the hardware, or at least like my brain need to make sure I understand this weird part of the language, right? That's the analogy is basically that's the CISC ISA. I might have instruction that you're not going to use it for the most of the time. You're not going to use that instruction. But because the instruction exists in the ISA, your hardware, when you build the hardware, you need to make sure that you can run that particular instruction. So for those 1,000 instructions, there has to be dedicated hardware to run those, or some kind of design to make sure I can support that instruction. But the reduced ISA might just be like 100s of instruction, which means that my hardware is simpler, right? I just need to make sure I support all those 100. And now, once you support those 100 instructions, you're going to have a lot more transistors left that you can use for optimization. So it basically means that do I want to trade off like between a fancy instruction that are really fast because I have a hardware for that in the CISC ISA, or I would dedicate more transistor to make sure my CPU can do a lot of things really fast, and that lots of things is only 100s of instruction, right? So definitely there are trade-offs between the two things, and as you can see, many of the CISC ISA might have some flavor of the RISC ISA nowadays, or the RISC ISA might have some flavor of like, I want to support complex instruction, and here's how you can define it. RISC-V has extension that you allow to add more command, if you will, right? Now, when I said instruction, right, this is the most basic elements of the interface between even human to the computer, right? Software and hardware, because you program, human program software. The main component are two things, the opcode and the operand. Think of it as a human spoken language, all right? It's like when you think about human language, how do we structure the sentence? How do we structure our sentence? How do we talk? What are the majority of the things you need to add in your sentence to make sure it's understandable? Can someone tell me what's the most important thing? All right, come on. Not hard. Definitely not hard. What do I need in a sentence? Exactly. You need at least the subject and the verb, right? Like, I'll use my daughter as an example. Now that she understands some verb and she understands some object name, she can string together the object name and the action, the verb, and now she can communicate, right? It might be hard to translate what she's trying to say, but good enough, right? Same thing goes with the computer. The opcode, think of it this way. The opcode, think of it as that's the verb, that's the action. The opcode tells what's my action. The operand is the subject or the object who is going to perform that action. What are the objects that get performed that particular action? For example, if I want to say I want to add R1 and R2 and put the results in R0, right? Basically, the opcode will be the ones and zeros, the binary value that represent an add, and the operator in this case is just I want to add. So there'll be bits in your instruction that say that's the opcode that represent an add. Then the rest are the operand. All right. What are the other elements of the ISA? We talk about control flow versus data flow. So the sequencing model also can be a part of the ISA. Most modern ISA use control flow because it's much, well, I wouldn't say simple to design, but data flow ISA is way too complicated to design. All right. There are attempts from academia to try to design a data flow, like a purely data flow machine. Industry standard right now is still control flow, and we'll fake data flow inside the hardware. Okay, but the ISA still follow control flow. There's also processing style, right? How many, when I string together an instruction, which imagine when I talk in a sentence, how many subject and object can I add in one sentence? So that's the addressing machine. Zero address machine means that I cannot really put in any object. It's a stack machine. I can only do operation, then push, pop, push, pop, 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 push, push. Whatever operation on the stack. Quick note here that even though I say push A or pop A, that object is just a single value, which is kind of always by default, you cannot really change. So the key here is you cannot really change the object. It's just the data that you put on the stack. The one address machine, we call this the accumulator machine. So both zero address and one address machine are like ancient machine. You don't see it now. It just doesn't exist anymore. We have way more transistors to implement the two address and three address machine. So no one designed it this way. But the one address machine, what are the operation you can do? Basically, you can do operation and accumulate. So you can access the data, load to this object, store the value to this object. Then you can do accumulate. Go up, go up, go up, go up, or go down, go down, go down, go down. Which is, again, this is not convenient at all. Right? So with the accumulator in the one address machine, again, Your option is you perform some operation on the accumulator, and that's not convenient. All right. The two address machine, and one good example of the two address machine is Intel and AMD x86. Those CPU use the two address machine. The way the command work is like OP, the operation, source, and destination. For example, I can do add. And in this case, what I'm trying to do, the EDX and EAX in x86, these are registered. Think of it as a variable, right? I want to add the two numbers. So what happened here is I will basically add EDX and EAX together. So both of them are the source. EDX plus EAX, then I overwrite EAX. So you overwrite the old value. So that's a two address machine. We use this in x86. Then many modern ISA also use the three address machine, which is actually, to be honest, in my opinion, it's more convenient to program. You put three things. If you need two source, I want to add two number, source 1, source 2, you add them together, and then you specify where is the destination. So the three address machine, you can specify the source on both source 1, source 2, and then you can specify the destination. For the two address machine, you can only specify source 1 and the destination, and then source 2 will assume to be destination as well. So you take source 1 with the destination, do some operation on the two inputs, write the result back to destination. Okay. What are the trade-offs? Why do we have this design? Space, code size, performance, and also number of executed operations. Okay. Again, opcode and operand, I said that already. Then there's an operand specifier, which is what we call sometimes addressing mode. It kind of dictates what does each of the bit represent in terms of, I want to get to that address. How do I get the address translated into some, like, let's say I use a pointer. How do I represent that address in my instruction? So that's the addressing mode. Data types, these are things that the bits actually represent. Is it integer, floating point, character, binary, or decimal? It can also represent complex structure for the sys, like an array, for example. Some sample in x86 and wax. Wax is kind of like the extreme also of the sys. Things that are complex that might be available in a complex ISA can be things like, I want to compute a convolution, or I want to load an entire array into my memory, or I want to do some pre-built function that is kind of always available in my sys. For simple instruction, these are something obvious like add, XOR, load, and store. It's a typical instruction you see and use a lot of time. All right. And complex operation can always be built from simple instruction. And to be honest, if you can do an and you can do a not, you can do everything. Also, you can do an or and a not. You can also do everything. So basically, as long as you have the logic gate that can do and not or not, you're good. Okay, we can build adder, we can build multiplier, and from that point, when you have ability to build adder and multiplier, you can build whatever. Okay. There are also trade-off. Complexity of instruction. For example, you can have a denser encoding. Instruction is smaller. Each command is going to be more dense. Think of it as when you say some sentence, there's a lot of internal meaning to the word you say. So that's a dense command. This, for the complex instruction, this can simplify the compiler because there's always an instruction to do something, right? For the reduced instruction or in the RISC ISA, this simplifies the hardware because it only has to perform simple instruction. It also have a higher tendency that you can clock your CPU higher, and also allow more compiler optimization. And this means that as the machine gets better, reduced instruction is going to benefit more from compiler optimization, because we have a lot more advanced technique in compiler to keep optimizing your assembly into a better version of the assembly that do the exact same thing but faster. All right. Now the next topic I need to talk about is called semantic gap. What is semantic gap? Basically, this is a gap between your software that you write and the ISA, right? One thing you can do is you can have a large semantic gap. Basically, it's a little big gap between your software and the ISA. What are some examples of this? My ISA only have the option to control the signal. Look at how you control quantum computer. For example, this is like a huge semantic gap. You want to write some program, and your ISA is like, well, I cannot really do a lot of things. I can only command what to read, what to write, and that's it. These allow more compiler optimization, also mean more work for the compiler to actually translate your program from the software to the machine code. A small semantic gap means that ISA is going to look like a high-level language. Whatever you write in software, there's always going to be something similar in the ISA to support that command. These allow more application-specific hardware optimization for the specific command that you want for your exact software that you're running, right? There's also translation between one ISA into another. For example, if you buy a MacBook nowadays that comes with the M1 and M2 chip, right? Here's the thing. That chip uses ARM ISA. Your friend's computer uses x86 ISA. How do I make sure that the same program developed by, say, Microsoft, like Microsoft Word, or even what we're using right now, Microsoft Teams, run on the different ISA, right? Basically means that we just need to change the semantic gap by either recompile or basically do some translation from one ISA code into another ISA. Okay. And the high level data types also can provide some benefits. For example, I can have a high level data type that represent a list in the ISA, right? I can say that if you want to implement a list in ISA, this is how you specify it. But the downside, again, because if you want to expose that to the ISA, it means you have to support it. It means that the hardware now need to understand what is a list, right? Because, I mean, to be honest, the way you use a list right now, the hardware doesn't really understand whether that's a list or not. It just follow the software. Whatever the software tell you, okay, do whatever you want to do. And then the implementation of the list is done in the software, right? This affects semantic gaps. Data types are tied to the semantic level. Smaller semantic gap means that basically your data type might be implemented by default in the SA for multiple data types. A large semantic gap, I might just want to support integer, floating point, character, and that's it. And maybe Boolean, right? And that's all. Memory organization is another element of the SA. How do I organize the data in the memory? How many different unique locations in the memory that are being used for example, the I/O, the network, storage, the swap space, or even things like the space for kernel's data versus user data, and for each of the user that use the machine. So these are called address space. Addressability means that if I want to go access my data, can I go access each byte individually, each bit individually, or in a 64-bit or 32-bit byte addressable manner? All right. One quick exercise that you can do is basically, if I want to add two 32-bit number, but with byte addressability, I can only go to each byte, not the whole 32-byte chunks. How do you do that? Or if I want to add two 8-bit number, but I have 32-bit addressability, how do I extract just the 8-bit and add them together? So think about this too quickly. We'll kind of for the purpose of the lecture, because we're having a break as well in the middle, so I'll just keep going. All right. You watch the video, you can pause and kind of try this as an exercise. The next thing is, how do I support virtual memory? This is one of the crucial parts of your system, where when you program, the address that the program is using is called virtual address. And the actual location has to be translated into the physical address. How do we support that? We'll go into more detail about these things in the future for this class. All right. That's sort of big versus little endian. So if you use IoT device or you in the embedded system class, is one of the things that you might have to be careful about. Where is the most significant bytes in my data block, right? Also, the next thing I have to talk about is what we call register. This is one of the most important, well, it's a really important thing in your CPU. Think of register as a really fast temporary memory. Some ISA will have a lot of this, some ISA doesn't have a lot of this. Some of them might be bigger, some of them might be smaller, depending on the design. The benefit is this provides a really, really quick way to access your data rather than going all the way to your DRAM. So there's going to be a really, really fast memory that you can use for a few bytes of data that you have, right, in the CPU. And register kind of evolved over time. Back in the day, because we don't have a lot of things we can work with, we start with what we call accumulator. I start with a number, I can add a number to that. That's why we call it accumulator. It just store a number and you can add numbers to it. Then you can use accumulator and the address register. Now you can point to locations. And then you can accumulate. So you have one accumulator and one address register. This guy point to where in the memory you want to access. This guy just do the adding. Now your register becomes general purpose register. Think of it as a temp variable in your program. You can use whatever, like you can do anything with it. It can be used for all purposes. Now it's really easy to use and manipulate. And the range can be from a few register to a lot. For example, in the Intel IA64, which is now, I think they no longer support this, has 128 register. All right, and no one used the accumulator and like the two bullet points anymore. Everyone used the general purpose register nowadays. All right. The next thing in addressing mode, what does it mean? It's define how do I obtain the override. For example, I can say I want to load the value at certain address, right? For example, I can do load value at address 10 into register R0. I can write it this way. Load with the flat address, right? 10 represent a flat address, that's address 10. I can do register indirect. So instead of putting a number 10, I can say, hey, I put the address into R1 first and I want to load wherever it's R1. That becomes the address. I go to address R1. I look at what's the value over there and then I put into R0. I can then also do display space. For example, I can start with R1 as an address, then I add some offset. It can be R1 plus 10, for example. I look at that location R1 plus 10, whatever the data I saw, I put that into R0. So that's called addressing mode. How do I go to my data? And there are multiple options for this. Each ISA has a definition of how you can get your own addressing mode and how do you use it. How do you use it? For example, in the Intel architecture, in the x86 the x86 64-bit architecture, the way you do this is you have offset followed by a parenthesis. Inside there can be three things: base, index, and scale. And your address is going to equal to offset plus base plus index multiplied by scale. Why do we do it this way? You can then manipulate the index and the scale to quickly go through your array when you write a program, right? So that's how x86 handle addressing mode when you have to handle a lot of arrays, which just happen to be a lot of your programs. And there are different benefits for each addressing mode. For example, some of the addressing mode will reduce the number of instructions, the code size. Some of them won't work better with, say, array or even things like a linked list or pointers chasing application like a graph. Downside can include more work for the compiler. When you build the compiler, you need to then figure out what addressing mode should I use for these programs, for these line of code to make it the best as best as possible. More work for the microarchitect because I need to build the hardware to support all the modes I want to support. What else? I might specify how do I interface with the I/O? How do I use things like memory map I/O? This is the region of memory that's mapped to a certain I/O devices, like a disk or a network device. How do I use special I/O instruction that deal with certain I/O devices? How do I handle user versus supervisor or the user versus kernel? Tell who can execute what? How do I handle exception? How do I handle interrupts? What are the procedures to follow when something goes wrong? Or when some external device requests something like you type on a keyboard, it can be vector or non-vector interrupts. So I'm not going to go into detail on this part because it's more like a system topic now that about like how does the OS handle interrupts and all those things given the essay. Also how to handle virtual memory and access protection. There are also different classes of instruction. First is the operation. Sometimes, in many cases, I call this compute instruction. The thing is for the compute instruction, the main thing is I just need to process the data. These type of instructions just process the data, like add, multiply, all right? Take the operand, perform the operation, done. The other type is called data movement. Sometimes we call this load and store. Sometimes we call this memory instruction. Basically, these move the data between your memory to the register and from the register back to the memory. Okay. The last type is control flow. This dictates how you handle things like if else or for loop. That's why we call it control flow. How do we change the sequence of instruction that we are running through if else and for loop that the programmer is writing? How do you support that kind of operation? Okay. There's also the load store architecture versus memory architecture. Load store architecture means that if I want to do something with my data, I need to make sure I load that into the register first. Again, load store architecture basically means that if I want to do an add or a subtract or multiply, the data has to be loaded into the register. Most risk or reduced instruction set ISA follow this model. Memory to memory architecture means that I can say, I have the address here in the memory, address here in the memory. I want to do operation on these two addresses. You can do that. So instruction can operate directly on memory address or memory location. You don't have to always load that into the register. What happened in reality is that basically the data is loaded anyway, right? So, I mean, that's the reality. That's how we implement this memory to memory architecture. Back in the day, it might not. Back in the day, that might be an adder that dangling and like just do an add from the memory. Because back in the day, registers are not fast. But these days, CPU is a lot faster than memory. And the way we handle things is we load data into the CPU, to the processor register anyway, right? There's also instruction length trade-off. Some assembly language has a fixed length instruction, like a RISC-V ISA. These, sorry, I always have this. Decode, all right? It's easier to decode an instruction. You always, for example, grab 32 bits at a time. Because I know the instruction length is always 32 bits. Because of that, I can always just get the 32 bits and then decode what am I doing here. Get the next 32 bit, decode what am I doing here. Get the next 32 bit, decode what am I doing here. Easy to also decode multiple instructions at the same time. For example, if I have here, let's say this is my instruction stream, right? Basically, what do we mean by instruction stream? It's just a bunch of instructions. I am supposed to run this one, instruction 1, followed by instruction 2, followed by instruction 3, followed by instruction 4, and go that way. And because I know that each box here is 4 bytes or 32 bits, right? Again, this is 4 bytes. It means that while I am trying to decode instruction 1, the first 4-byte block, I mean, if I have a ability to keep getting new instruction, I can then fetch instruction 2, 3, 4, and 5, and 6, and try to decode all of them in parallel. Right? Because I know each box here is 4 bytes, so I know the location exactly where's my next instruction. But then, if the size of the instruction is fixed and it's too big, then it means your code gets bigger. Because every time, every line in assembly is going to be some fixed size. And it might be harder to extend in some cases because you just ran out of bits. There's nothing you can do. You cannot add any more instruction. So here is the RISC-V architecture instruction format that tells you, OK, if you use the 32-bit format, here is how it works. The opcodes, for example, will always be in here. So this is the opcode. This tells the action. So whenever you get the instruction and you look at the first 7 bits from bit 0 to bit 6, you can tell, what am I supposed to do? Right? That simplifies a lot of things. And it, as you can see here, RS2, this is source 2, and this is source 1, right? And this is destination. You note the position. It's always on those bits. It means that when I get the instruction and I look at these particular bits, I know exactly the action, the object, the subject, verb, and object. Now I can finish the instruction really quickly. All right. So you can also have a variable length like x86. It's more compact, which means that your code is going to be smaller. This kind of work well in the back in the day when we don't have a lot of memory to work with, right? It's harder to decode because you cannot really tell how long is my instruction. One example of that is x86. The same instruction, the VEX instruction. There's a 3-byte version and a 2-byte version. The 3-byte version means that if you get the first byte and it ended with 101, it means that just get 1 more byte and you're done. If it ends with 100, it means that get 2 more bytes. Now you know what you have to do and you're done, right? So the steps in trying to figure out what is my action, how do I actually get to finish this particular instruction might take longer. So here is also another trade-off, uniform decode. As you can see from the RISC-V example, opcode is always on bit 6 to bit 0. That's uniform decode. It simplifies the steps when you have to decode, and it simplifies the hardware design. All right. Non-uniform decode, the benefit is it's more compact. There's no unused area. And it's easier to extend. You can basically pick more bits from the field that you're not using. But then your decoding logic is going to be more complicated. All right. So that kind of wraps up the topic of ISA. Any questions so far before we move on to the single cycle architecture? So we're now diving deeper into the hardware design. If not, we can keep doing a Q&A during the break. Let's do a quick break. We do have quite a lot of time, so let's do a 12 minutes break. We'll resume at 10 o'clock. If you have any questions, type in on the chat. I'll get back and answer your questions, all right? I'm going to go get some coffee and be right back, and then we'll come back and talk about single cycle architecture, all right?